It's time to take a look at the 2024 AP Chemistry exam questions. The free response questions have just been released, and now we're going to walk through the answers. Hi there, my name is Jeremy Krug, and this is my walkthrough for FRQ question number 4. I need to let you know that I don't work for College Board, and this is not an official answer key. You'll need to wait a few months for that. I'm just a guy who's been teaching AP Chemistry for the past 24 years. And if you're getting ready for next year's exam, then check out my full AP Chemistry course videos right here on YouTube, as well as my comprehensive review materials, along with exclusive tips and tricks over at ultimatereviewpacket.com. Now, let's get started. Free response question 4 is a shorter question, which is worth 4 points. And here we have an experiment. It says a student performs an experiment to determine the specific heat capacity of a metal. The student places a cube of the metal in boiling water, so its temperature will be 100.0 degrees Celsius. The student then places the metal cube into a calorimeter that contains water and records the highest temperature of the water. A data table and a diagram of the thermometer at the highest temperature are shown. So there's the data table, and we have a zoom in on our thermometer, and part A asks, what should the student report as the highest temperature of the water? So once again, we see that we have calibrations on the thermometer to the nearest ones place, and so the thermometer's temperature is reading somewhere between 38 and 39 degrees Celsius, so we have to estimate one digit between those lines. That's how you read any graduated device like this. So it looks like it's pretty much in between, almost halfway in between those two lines. So I think it's safe to say that the temperature is about 38.5 degrees Celsius. So that's the answer to part A. Now part B says a particle level representation of water molecules in the calorimeter before and after the metal cube was added is shown. The length of the arrows in the before diagram represents the speed of the water molecules in the system. In the after diagram, draw an arrow for each molecule to indicate how the speed of each of the molecules changes after the metal cube is added. So notice that in the before diagram, we have different molecules moving at different rates, but notice that when the molecules are warmer, after we drop the metal cube in there, the water is going to get warmer, which means that the molecules, on average, are going to be going faster. So I've basically drawn each of the arrows a little bit longer than they were before. They don't all have to be the same length, but they do need to be longer than they were in the before image. So that's part B. Now moving on to part C, it says, assuming the metal transfers 2,940 joules of thermal energy to the water, calculate the specific heat of the metal in joules per gram degree Celsius. So this sounds like a nice Q equals mc delta T example. And if we take a look at what's transferred, it says that the metal transfers that number of joules. So that means that the metal is actually losing 2,940 joules. So I'm writing this as a negative 2,940 joules in that Q. Now the mass, if we go back to the problem there, it says that the mass in that data table was 98.1 grams. So I'm going to put 98.1 grams in for the M. Now we're trying to calculate the specific heat. So that's our C, which is our unknown. And then we notice that the temperature of the metal dropped, didn't it? It started out in boiling water, which was 100 degrees Celsius, and then it dropped. And it said that the final temperature of the water was 38.5 degrees Celsius, so we can assume that the final temperature of the metal was also 38.5 degrees Celsius. So our delta T is final minus initial. It's 38.5 minus 100. So we have to be careful with our signs here. When we multiply, or actually let's subtract that first, and we find that the temperature dropped by 61.5 degrees, we can do a multiplication and a division, and we find that the value for C is 0.487 joules per gram degree Celsius. So that's the specific heat capacity of the metal. In part D, it says we have a second experiment where 2,940 joules of thermal energy is transferred from 98.1 grams of aluminum, which has a specific heat capacity of 0.897 joules per gram degree Celsius. Explain how the magnitude of the temperature change of the aluminum compares with the magnitude of the temperature change of the metal in the original experiment. Well, one thing I notice is that everything is identical except for the specific heat capacity. So we have the same number of joules being transferred, the mass is the same, and of course our specific heats are different. And so the question is, how is the temperature change going to be different with the aluminum as opposed to this other cube of metal we had in part C? Well, I noticed that the aluminum has a higher specific heat capacity. Now, it's helpful to remember what specific heat capacity is. Specific heat capacity is basically a measurement of how well a material resists temperature change. So when aluminum has a higher specific heat capacity, that means it's going to resist temperature change much more effectively. So basically the answer is it has a higher specific heat, so it's going to have less of a temperature change than that original block of metal. And we can just say that. Now, if you want to do a calculation, I think that would work as well. I think that you actually could plug into Q equals mc delta T, and we have the same number of joules being lost by the aluminum, the same amount of metal, the specific heat plugged in 0.897, and if you solve for delta T, you'll find that with the aluminum, we have a drop of 33.4 degrees compared to a drop of 61.5 degrees, which we had with the original block of metal. So I think that you could answer this using a calculation. I think that you could answer this with the concept of what specific heat capacity is. So we have a couple possibilities there. I hope you enjoyed this, hope you learned something, and I hope you did well on this question. If you did, great. I hope to see you again very soon when we're going to take a look at question number 5. Thanks for watching.